understand how to like represent on paper. Like I don't know. I feel like I don't understand what's going on with it. Like fully. Is there any like any way I could like practice or like I don't know if there's a better way to understand it. I just don't really get it.
Yeah, I mean, why don't we go over it during recitation?
Okay.
And then I can give you practice problems.
Okay. Thank you.
Do you have a stapler?
No.
I took a martial arts class when I was like, oh, sweet, we're gonna be PJJ or judo or something. When we get there, and the dude's like, he's a black belt in Aikido, and I was like, oh, that's not even legal for sure. He starts like having us like meditate and do like all this hand stuff. And we're like, so when do we get to like practice sparring? And he's like, oh, there's no sparring in Aikido.
Even a meditation class.
I was like, then why are you putting me in class in martial arts? I didn't. He ended up canceling the class after one quarter because everyone stopped showing up. Because I know for the civil program it's 57. And that class.
Kind of boring that
You translate through Oregon Health?
that's the point.
Students. Professor Room's awesome, but I don't know why the business department's teaching writing class.
Yeah.
Oh, she wanted to take her. Like, she's like, this is a job. And you're like your paycheck. Your paycheck rate is your paycheck.
That's crazy. That's the crazy thing to do.
I think she's doing something really good at learning how to not just write technical documents, but how to make it look really nice. Like nice.
Makes sense.
And now every report I do is kind of nets out with title page, table of contents, appendices, glossary. And it just looks nice. I'm like learning how to use sections and stuff. Or not, the headers. Barely passed the class. I remember one night I spent 8 hours going through because you have to do an interview with a specialist and whatever your documents are on. I went through an hour-long interview, transcribing it because I couldn't read programs to transcribe audio files. Oh my God. Like having to go back like 10 seconds.
Oh,
Because you have to do your transcript of your interview.
yeah.
I think that's pulled up like 15 pages. would recommend taking it during a term where you're only taking 12 credits. So you're like really focused on it.
That's a lot. Oh. I took, I got really sick during the final.
Interpersonal? Interpersonal communication?
Yeah. I had to drop out of economics.
What's your one or two?
201.
With, Campbell? Wait.
I took it online too, which is not a good thing. They only offer it online.
I do have some stuff to turn into. Do you happen to have a stapler?
No.
You don't have a stapler?
No, not down here.
You know if I like, during your recitation, if I go staple and run back to you?
Yeah.
Do we get these back after they're graded?
Yeah.
Okay, sweet, thank you.
I need to grab some stapler so I can take my first class. I just put my on the first one I have, I just put my name on it and what it was. So far in physics, it's all out for race, right? It's going on for
No, he teaches you the derivatives, but he's like, the way you use the alpha.
All the derivatives will give you is the equation in the algebra, right? Yeah.
Do you remember computing chapter 3? Because I don't think I was here when you passed out the paper.
And when you take physics, it's easier to, it works on these problems out.
Thank you.
I only messed up once. I dropped 8 points because of excuse me.
You know what I meant,
All right. Let's get started. And so just a quick announcement. If you look at the Blackboard page, I put a link to this Estee Lauder internship. And so applications just opened up for Estee Lauder for 2025. So I thought I'd post that. And so lots of, interesting internships. So not just for STEM, but, you may be interested in that, but also kind of AI internships, cybersecurity, communications, so, right? Lots of opportunities out there. So just putting that out there. And of course, don't forget NSF, right? Again, start looking at that. I don't know when the applications will, start refreshing, but keep an eye on that since, getting jobs and internships, that is what's important. All right, so let's continue. So we were discussing our first ionization energy. So again, just specifically removing that one electron. And so then we said we'd looked at the general trends. So of course, again, right, our ionization energy decreases as we go down. So that is shown both in the chart, but we can see that again with the reactivity, increasing reactivity of our alkali metals as we go down, again, as that one electron is more readily ejected from our less of our effective nuclear charge. And then we said, okay, it increased as we went across and again filled in that same shell. And then of course, right, the noble gases have a high ionization energy as they have the fulfilled octet. And so again, just kind of the summary of that. And so then we looked again at this interesting scenario where, okay, even though we're moving across the periodic table, again, we had that energy price there, right? So oxygen has a slightly lower ionization energy than nitrogen, even though it has more electrons, again, because of that pairing. And this is, kind of, again, the theme of the course is like looking at these orbitals. And so right now, we're just looking at the atomic orbitals, so just of an atom. And so again, as we move, we'll talk about molecular orbitals and how that all relates to bonding and all the depth of information that tells us. And so then we want to look into the successive ionization energies. And so the next thing is, well, each successive ionization energy, and it tends to be increasing, but then there's also this jump pattern. And actually, I like the book for this. And so if we look at the book, and the book has several of these diagrams, and so we can kind of piece through it, again, what it's showing us and what this is telling us about the electron shell, right, and the structure. And so this is lithium, and of course, right, lithium just has 3 electrons. And again, you can kind of see, okay, we have our first one, and these are just our ionization energies, so first, second, third. So the first one is down here. And again, the pattern that they're trying to get you to note by graphing the log is the jump here. So they're pointing out, okay, there's a jump, and then you have the next 2. So kind of suggesting, again, that first energy level, n equals 1, that 1s. So that's what that's suggesting. And it becomes more obvious as we look at the heavier ones. So let's keep looking in the book. Oops. And so this is kind of nice, right, with carbon. So again, this is interesting. So it has, again, our first 4 electrons are much easier to remove. So we have this grouping down here. And again, our gap, and then our next 2, right? So again, this is showing our shell pattern. And so just from these ionization energies, so this is, again, starting to show the trend of, again, our shells. So we're trying to piece back out the s and the p orbitals from this. So there's, again, neon. I think there was another one that was cooler. So then I like, right, potassium over here. So this is interesting because, again, we're seeing those shells. And so let's pull up our periodic table as well. So, okay, potassium, right? We can look at our electron configuration. So the valence electron, we can say is in 4s1, right? And then so going, okay, there's the first, right, ionization energy. There goes the 4s1. And then count our next grouping. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's the next shell, right? Again, look at the periodic table. to kind of repiece where that's coming from. So that was now, right, the 3P that's showing, and our 3S there. Oops. So I bounce around, right? So our P, our S, and then again, another gap as we go down to the second main energy level, right? So now this is the second energy level with 1, 2, 3, 4, 5, 6, 7, 8. So again, right now that's stripping off this energy level here. And then, of course, the last two, the first energy level, we can see with those two groupings up there. So that's really nice, right? So again, you're really seeing the actual energy levels and kind of the structure of that. And again, those gaps are saying, okay, now we've gone into the next energy level. And so again, from our notes, we also want to get this numerically. So that's what's shown here. And so again, kind of looking at these trends. And so we can start with sodium. And again, I'll now refer to this periodic table. So just follow along. Maybe get out your periodic table, right? So we're starting with sodium over there. And then working our way across. Okay, sodium. And we can piece this for ourselves. So of course, we know it has one valence electron. And then it's pointing out the gap here, right? So we started with 496, and then we jumped to 4,560 for our ionization energy. Again, these are all in kilojoules per mole, but that large jump is telling you, okay, now we've gone from the valence electron to the core. And then, okay, so now we go over to magnesium. So now we're on magnesium. Okay, we know from our periodic table, so I'll pull up this one for a second. Okay, we know it has 2 valence electrons, right? So now we can see that again. So we have, okay, 738, 1450, then, okay, another huge gap, right? So from 1450, then it jumps up to 7,700. So again, that's telling you, okay, we went from our valence electrons to our core. And so if you were given just this data too, without the element, you could probably piece together, okay, this is an element that has to have 2 valence electrons. And so you may not be able to identify that it's necessarily magnesium, right? But it has to be something in that column then, right? So if it's not magnesium, it's calcium, strontium, etc. Anything with 2+, so 2 valence electrons. So aluminum, again, right, note that same pattern. So 578, 1820, 2750, boom, 11,000. Big jump there as we go, again, to our core electron. So again, reaffirming that aluminum has those 3 valence electrons. So silicon, again, right, we're just going across. So 4 valence electrons for silicon, and again, we see that huge gap from 4,000 to 16,000. And so again, just kind of appreciate that as we keep going. So does that kind of make sense how this is going to work out? And so on a test, right, again, I would give you some data that could just look something, you know, like this row with no identity. So, right, you wouldn't know it's sulfur, but then, okay, you start examining it and you look for the crazy big gap. And so again, right, this one, they were all just going up by thousands, pretty steadily, roughly, and then boom, huge jump. So then you know it had 1, 2, 3, 4, 5, 6 valence electrons, right? Because it's right before, right after the 6, I mean, where it's the jump, right? So you know the 6 is the last valenced electron, and the 7th now we're in the core. And so then, right, then you could piece together, well, this has to be something with 6 valence electrons. So again, we get sulfur or anything, obviously, right, in that column. So does that make sense? Does that kind of follow along? And then the other thing, again, to note is you have to write a separate equation for each one. Let me see if we have. There we go. I think it's, we scroll back up. So remember, we said we have to go to each subsequent one. So right, the second one is M+. So at each one, you're just doing each successive ionization, right? So you start off with metal plus our first ionization energy gives us M+ there. And then this one, right, is now starting at M+. Now our E2 gives us metal 2+. And then so on, so forth, right? So then you start with metal 2+, third ionization energy, metal 3+. So that's just how that continues, right? So you can follow that pattern and write your equation for that. Any questions on kind of this so far? And so then we're kind of wrapping back around now. And so now we're kind of back at Lewis dot figures, which then we can just kind of simplify now. And so, right, we said our Lewis dot representation is another way to kind of do our electron configuration. And so let's go over how kind of I like to do it and think about it. But then we'll just go over the pattern, right? And then you'll just see boom, boom, boom. It does this repeating pattern. And this is going to be really powerful for, again, the rest of this course. And so let's start off with, let's do oxygen. So just write the electron configuration for oxygen for a second. All right, so what do we get for our electron configuration?
We have helium at 2s2. Oh, and then 1p, I think.
Oh, 2p, remember?
2p.
Yeah, and then 2p.
Oh, the p's don't drop. Okay. Drop down. So 2p4.
2p4. So that looks good, right? Everybody get that? And I like the abbreviated form there too, so good practice. And so then what we want to do is kind of retranslate this. So now let's think about it. Okay, it's our 2p's, right? So now I like to write it in this kind of form. And again, right, your book does other representations, right? It does it to the side and these boxes, same thing, it doesn't matter. I just draw it this way to kind of, again, show some sort of relative energy levels, again, indicating that our S is lower. And I've left off the 1s, you know, it's the core, it's fine. And so now let's fill this in. So again, we started our S, our lowest energy, so 1, 2, then our 4, so we said we need to put 1 in each degenerate P before we pair. And so now we have this little diagram. And so what I like about this is, and how it translates to our Lewis dot structure, is that what we have, you know, 4 orbitals total that we're looking at, which kind of translates to our kind of 4 sides for our Lewis dot structure of our little atom here. And so I just want to draw the same thing. And so what I mean by that is I'm going to pair 2 electrons to signify that, yes, we have 2 paired in the 2s. Then we want to pair another 2 that shows, again, now we have 2 paired in our p. And then we have, of course, our lone 2 electrons. And I think some people were seeing this already yesterday or Tuesday right? So now we're seeing, okay, well, we have those two little dots here. So now it's either signifying that it wants to gain 2 electrons, right? Or if it's in a molecule, it tends to make 2 bonds. And we're going to see that, right? And so this is kind of going beyond Lewis dot structure for a second, but it's just showing you how powerful this basis is. It's like now we get a lot of information, right? Yeah.
So on the periodic table, the little numbers in the top right of each box, those are kind of telling us how much electrons they want to gain or lose.
Oh, yours, so yours have like little, so like for fluorine, it probably just has -1, but then chlorine, it's like +7. Is that what you're talking about?
Yeah, the +1, +5.
So those we're gonna like hold on to. So really, we want to just write, okay, we're gonna treat as -1 again in an ionic compound. Where the 7s and the 5s come from is from like formal charges in compounds, but we're not measuring that right now. So if we have like chlorine, like a chlorine-based compound, or like, I3, then that's where we get like those weird positive formal oxidation states. So that's where those numbers come in. But for transferring electrons, just stick to the -1. Like you're right in that, it does kind of relate to how many electrons it wants, but really, right, chlorine's never going to lose 7 electrons, realistically. It may kind of do that in a bonding scenario where it's formally 7+, but for ionic compound purposes, it's always -1, and then this is -2, and then this is where that weird kind of switch happens. But again, the +5 is now more formalities. All right, so let's look at this, and we can kind of see this pattern. And so this is, again, our Lewis dot representations. Of course, hydrogen makes sense that it's just 1 dot. But then, of course, right, we see lithium will also, in that same column, right, has 1 dot. And again, that's reflective of its electron configuration. So these are all NS1, and so all the group 1s are going to have just 1 dot. And so you can simplify this, right? So now we can say, okay, well, all our group 1s are all going to have that same NS1. So we can write our electron configuration and our Lewis dot structure, to reflect this. And so again, this is telling, right? This is, again, why we can make salt. So sodium chloride, why, again, they tend to be in that 1+ oxidation state. And then so notice, and I like your textbook for this reason. So beryllium is then shown, and helium as well, with 2 dots on the same side, right? And I agree with that because that is showing its electron configuration, right? It's showing that we have NS2. So we can think about beryllium's electron configuration and really any kind of group 2. And of course, we'll put helium in this category. So beryllium, calcium. So they all should be drawn like that. Again, reflective of our NS2. So we can write that on our periodic table, NS2. Again, right, wherever you need to write this to put all your helpful hints so that you know what it always is. Because again, this is like your foundation cheat sheet now for how we're going to build molecules and figure out everything else. And so that being said, you may find a book or an internet resource where they do draw it like that. But again, I disagree with that since it does not have a chemical background. Like it's not based in something, right? And then, so boron should be drawn like this with the 2 dots on one side. But then this starts to get to some of the exceptions. And so for group 3 now. So now we're at NS2, NP1. So it's probably most proper to draw them like this, again, reflective of their electron configuration. But I will say that I will also accept anything where the dots are kind of drawn like so in this hybridization, because now this is reflective of reactivity. And again, we'll get to this. So, and so this is just something that, again, we're going to be learning, that basically a lot of these group 3s, they do not make ionic compounds like we might expect. Again, they make these covalent structures that are trigonal planar. So I'll at least add that for now. And so that's the same with boron. So again, I would accept both of these answers on an exam. But you may want to note, that you do understand that this is due to hybridization. And you can add this term, which we'll come back and explain what hybridization is. We're still kind of working there. And so just continuing the trend. And so carbon is the next exception, so we should talk about that. So group 4. And it's funny because I drew it kind of properly. So group 4, so now that's NS2, NP2. And so the one exception, which is funny to me that they didn't draw it like such, is carbon. And so carbon is, of course, famous for hybridization. And so this is called sp3 hybridization. And going into how carbon always makes 4 bonds. We'll come back again to hybridization. So it's only appropriate, though, to draw carbon like this, because, again, it's reflective of its reactivity, and we could get into why we're probably carbon-based life forms, and it's because of this hybridization and carbon being small and carbon making all these combinations with itself. But then what about the other ones? So the heavier analogs of group 4 or 14, however you want to call them, they do not do this hybridization as readily. So then the heavier ones should follow the electron configuration pattern. And again, that's reflective of how they can be isolated. And so you should draw silicon like so. And again, we can isolate silicon as a divalent species. So yes, this is reflective. And so that would be the same for germanium. And so again, you can write that wherever on your periodic table, whatever is most helpful. And just remember, carbon is your exception. And so then group 5, we can write our general pattern. So group 5, right, NS2, NP3. And so again, let's look at nitrogen just for a second there. So 2P, 2S. And so I'm going to fill it in. So 2 in our S, and then 1, 2, 3. So again, we want to draw our Lewis dot structure to reflect that. So that's why nitrogen has kind of just 2 paired. Then the other 3 are separate. And then so then this goes into either why it's a 3-, right, like the nitride in our ionic compounds, or when it comes to covalent, we'll often find that it makes 3 bonds. And then, right, that's repeated for a lot of the other structures. So obviously phosphorus looks the same, arsenic. And it doesn't really matter, again, what side you draw it on. Any questions so far?
So just generally looking at the periodic table, the groups tend to have similar orbital shapes. Is that?
Yeah, yeah, so then this is all, yeah, again, reflective of the shapes then, like you said, and yeah. So all of these, of course, yeah, use their p orbitals, they use it in the same kind of way, yeah.
Yeah, what if it's like a D or F orbital?
So what do you mean by that?
Like the electrons being there, are there more electrons in each? There are 10 Ds and 14 Fs. I thought that was like the number of valence electrons.
So I guess, are you asking for electron configuration, like what happens, or?
Yeah.
Like Lewis dot structures? We won't cover that in this class. So that's a whole separate field of study of inorganic chemistry and 18 electron rule, and you just, yeah, and then there's all these different rules and how you count them, and
Okay.
yeah, and then for other, yeah, I'll save what I'm going to save, actually. Save that thought. So then we'll continue. So group 6. So we saw oxygen before, so we did that one to begin with. And so again, right, they all follow that pattern. You can draw the dots any which way, right? So this is 3D. I forgot who else is in group 6. Oh yeah, selenium and tellurium. So again, they all 2 dots. Again, reflective of their reactivity. So we should write NS2, NP4. And then, of course, our last one are halogens. Well, we'll do our noble gases. Shouldn't neglect them. So group 7. So NS2, NP5. So of course, now they have 7 valence electrons, so only 1 missing. So again, we can tell that's why they either gain 1 electron or they form 1 bond in compounds. And so chlorine, bromine, fluorine, iodine all look the same. There's 7 dots there. So oxygen, 7. And then, of course, our last ones are our noble gases, and then, of course, helium, which we've stuck with group 2, but, right, just kind of have that as always your exception. So it's fulfilled by the duet rule, which is why it ended up right in our group 2S block, so it was fulfilled there. And then all our other ones, at least, again, will follow the basic octet rule, and so we'll draw them as such with 8 valence electrons. And so those, right, you can, of course, just fill them all the way. So 8 dots around them.
Helium only has 2?
Helium? Yeah, helium only has 2, right? So it just has 2 electrons max. Yeah, and then the other ones, again, we typically just look at, the valence electrons, right? So then, for example, krypton, even though it has all these d orbitals, we still just kind of look at those 8 valence electrons. Since, yeah, it's the outermost ones anyways that are going to be participating, but. All right, so we feel okay about Lewis dot structures. And then I think you might have done this in the homework, but then with ions, so like for calcium 2+, right, you can just write it like this. So this would actually be the Lewis dot structure, right? So of course, comparing to the neutral, it lost 2 electrons, so then we don't need to draw any around it, right? So you don't typically draw the 8, even though we know it's going to the next shell.
Are boron and carbon the only weird ones, or are there more?
Uh, well, and then like aluminum and gallium also do the weird hybridization, but yeah, it's mainly just those that do the main exceptions. All right, any other thoughts on Lewis dot structure? So hopefully this is kind of feeling like it's coming together and starting to make more sense with electron configuration and orbitals. And again, we'll keep kind of revisiting orbitals. But now we're going to take what I feel is like a step back, right? Because we kind of introduced orbitals. But now we need to understand just light for a second and how we can quantify and characterize, right, all our molecules and how quantum mechanics arose. And so, of course, right, this is the early 20th century, so they started trying to understand quantum mechanics, and a lot of this was like arguments, right, about light. So they were trying to understand, is light a wave, is it a particle, what is it? So they were doing, experiments, and then also trying to understand, of course, the parts of the atom. So they, I can't remember at this point, I think they had teased out electrons, but then it was more difficult to kind of figure out the neutrons, obviously, since they were neutral, so harder to detect. They just detected, of course, that there's a large center of mass from the Rutherford's gold experiments. If you remember that, I think, from the textbook. So that's how they discovered, right, the nucleus. But okay, we're still trying to understand the small, and so of course quantum mechanics too, they started noticing obviously behavior that deviates from what we consider to be the macroscopic prediction. And so we'll get into that. And so a lot of these experiments, right, we're trying to explore, again, what is light, right? So they were trying to figure it out. And so that's ultimately what led them to coming up with this wave matter duality concept. And so basically, and again, we'll kind of come to this, but the conclusion is since the electron is so small that it exhibits wave-like characters, which, again, we don't expect for something that has mass. And so this starts to get into now the difficulty of conducting these experiments and, again, what the issues were, what they were trying to tease out. And so, of course, electrons are extremely small, and we have this nice piece of trivia. So the number of electrons in a single speck of dust is higher than the people that have lived on Earth. And so, of course, again, the challenge is trying to directly observe the electron. And so, again, the challenge is that when you try to observe it, you perturb it. So it brings up that, right, you try to shine a light at the electron, and well, now you've affected its behavior. So that brings a challenge of how you study it. And of course, right, well, we're getting to this, but much of the behavior is, of course, determined by the electron. And so that all goes back to quantum mechanics and modeling, and also gives us back to the pretty pictures. So that's where we're ending with this. And so again, it tells us how electrons exist, and so this starts to get into, right, how we can map out our probability density maps. And so it is a light wave in nature, and so not the particle wave that kind of dictates some of these chemical properties. And so then this is where the probability density map comes into play. So again, we're just like appreciating the results of quantum mechanics, right? We're not trying to dive into and really dissect it, but just appreciating, okay, well, now we're understanding how we can model the electron, right? And it brings up this point. So the electron can no longer be viewed as a piece of matter, but as a cloud of probable positions. So this is what I always mean by probability density map, right? So we don't know exactly where the electron is, but we can map out kind of its probable regions, which again is how we know like what the s orbital looks like, right? So then you get this probability density map, and then it tells you, okay, it's in this sphere, and that sphere is the s orbital or a p orbital, et cetera, et cetera. Yeah.
So electrons aren't particles, but they're waves of light?
I mean, it's that wave-particle duality, yeah, but when it's talking about like the Schrodinger equation, that it's more the wave-like behavior that dictates it. So I think that's how all those equations arise from. But again, right, what we need to understand is that's how we get the pretty pictures. So that's what we're appreciating is like the data from it. And right, if you want to delve into the quantum mechanics, that's what like CHEM is for and physics, right? But we're just trying to appreciate the orbitals now and understand that. And so we also can get other things from this. So of course, right, our quantum mechanical model is how we can predict the periodic table trends. So again, we're kind of just doing that now in the oversimplified manner. So I always tell this to students that like once we get into it with MO theory and everything, you can do all these powerful computational calculations just on the back of the napkin. And you know, again, that's what computational chemistry is for, to actually run those calculations and show the data. But you as a working chemist can kind of sketch it out yourself and kind of make these predictions. So it's super powerful, again, the theory behind it. And so, right, again, it can help predict behavior, help predict color. And so this goes into transitions of the electrons and what makes things pretty colors. So we'll, again, get into this. And so again, it tries to also tell us why things are metals and nonmetals. So we've already kind of seen that, why elements gain certain number of electrons, why they're reactive. And so again, we'll see these patterns. And so to do this, though, we have to kind of understand light, though, and what information is being given to us in the form of light. And so light is a form of electromagnetic radiation. And so anything that is electromagnetic radiation just means that we have perpendicular oscillating waves, one for the electric and one for the magnetic field. So that's shown here. And of course, that's just, again, due to the electrons, but we just want to appreciate our field here. And so the other key note is, well, all electromagnetic waves move through speed at a constant 3 × 10⁸ meters per second. You can use 2.99 if that makes you happier. And so from this, right, oh, I'm about to switch. And so from this, right, we have our characteristics of the wave. So basically, right, how do we characterize it? So we have our wavelength. And so our wavelength, we'll learn, is related to the color. So we'll get into that, or again, whatever other type of wave it is, so how we, again, characterize it. Then amplitude is basically how, if we're talking about light, so how dim or strong our light source is. So our amplitude is given by our height of our wave. And of course, wavelength, we can measure from crest to crest or trough to trough, just putting those terms in there.
There's also frequency, right?
Yeah, frequency. And so, again, right, we're just looking at amplitude and wavelength right now. So wavelength, again, determines the color. So red, for example, we'll learn, tends to have a longer wavelength. So we see that here. lower energy, whereas like purple violet is shorter wavelengths, so we'll learn higher energy. And again, amplitude is just dependent of how dim or bright it is. And so colors, so this will be, again, what we're trying to get at, because we want to get the color, which will then tell us the wavelength, which will be related to the energy, but again, we're getting there. And so what we also need to understand about light is, so white light is a mixture of all the colors of the visible spectrum. And then we can take these instruments, or take a prism, a little spectrophotometer, and what it does is it separates the light into all its components. And so we can do this and see this in lab, and we will be doing this for fluorescent lights, but then with all the other lights. Yeah.
Does a prism split light into its invisible frequencies as well, like infrared and ultraviolet?
In theory, yeah, but again, we can't observe it, so you have to have some sort of detector. Or
Why are indigo and violet separate colors in light wavelengths and stuff? They look really similar.
That's actually historical reasons where somebody just decided, hey, there's going to be 7 of them, so yeah, we're going to distinguish between blue and indigo and violet. So yeah, if you can't make the distinction. Anyways, it's just based off of numbers anyway, so it's not that relevant, right? We're not going to be trying to distinguish between indigo and violet in this class. The point is getting the nanometers, the wavelengths, which we're getting to. And so the other characteristic, which somebody mentioned, was, of course, our frequency. And so this is just the number of waves that pass through a point in a given period. And so its units are in hertz, which is inverse seconds there. So just remember the inverse seconds later when it comes out. And so then the total energy is going to be proportional to the amplitude and the frequency. And so mainly the frequency. And of course, right, the more frequency the wave strikes, the more total force there is.
Can you go back up to frequency so I can write about these?
All right, so back to our relationship. So probably want to star or write down this equation. I'd probably write it down on your periodic table just because it's so useful. So mathematically, we have a wavelength, or excuse me, frequency is equal to the speed of light over the wavelength. And then, right, you can start to piece that out kind of mathematically for yourself. So C 3 times 10 to the 8 meters per second. So you can, right, do your dimensional analysis. And then divided by, and so you're going to have to convert your wavelength to meters in this case, because you'll probably be given something in millimeter or nanometers. So there'll probably be some conversion. Yeah.
What does V represent?
The little v is frequency, so it's like a curly V or something. So just make sure that this number is in meters so that, again, we can see how that's going to happen. So we're going to divide by meters. And then that is how you get your unit of 1/seconds, right, which is inverse seconds, which is hertz. So that's what I'm trying to show to you. Unit canceling is your friend. And if you forget the formula, right, unit cancel. It's always been my motto for physics. And again, so of course, this is what we're getting at. The speed of light is constant, so if we know the wavelength, we can find the frequency.
What do C and lambda stand for?
So C, remember, was the speed of light. So we had defined it earlier. Oops, not on this page. And I did post the link to the notes, so it's on the previous section. So that's just the speed of light, so that's generally c, and our universal constant. And then, yeah, the little lambda is for the wavelength, but then just note that, again, when you put it in the formula, to convert it.
Wait, so what does it start out as before you convert it?
Whatever it's given in, but typically it'll be given in nanometers, like, and you'll see that. All right, let's see if we can try this problem. And I think this will be it before the quiz. So calculate the wavelength in nanometers now of red light emitted by a barcode scanner that has a frequency of 4.62 times 10 to the 14th hertz.
Light is 3 times 10 to the 18th.
Sorry, what was your question?
Is it 3 times 10 to the 18th?
The speed of light?
Yeah.
It's 3 times 10 to the 8th meters per second. So this one, there's a few approaches to take, right? You could set up kind of triangle trick if you like that. And so, okay, if we're trying to calculate wavelength, cover wavelength, so that means we need to take our speed of light divided by our frequency. You could, of course, just algebraically do it, or of course, we can also set up our math and do our dimensional analysis. So we're trying to get to wavelength. So, right, we're basically trying to get to meters for a second. And so if we think about our units, right, if this is inverse seconds or, right, over seconds, then we just want to divide by this. And so that flips the seconds, right, times 10 to the 14. So that means that your second is now on top such that it cancels. So then we're left with our appropriate units of meters, which we'll have to convert, right, because it asks us for nanometers. But now let's at least get the number. So 3 times 10 to the 8th. And again, make sure you practice with your calculator. Make sure you're using the E button to signify times 10. And so now we get something like this. So 6.49 times 10 to the negative 7 meters. And then if we want to convert it to nanometers, so we can multiply it by 1 times 10 to the 9th. If I could plug it in properly, sorry. And so that also gives us 649 nanometers. .49, 7 meters. Any questions about that one.
Is heat also an electromagnetic wave?
No.
The light decays into
Huh?
light decays into heat.
Sorry, light, I just didn't hear you.
Light decay into heat.
So like if there's, that gets into like energy inefficiencies, you know, with the light bulb, so then you can say like however much is being lost to heat, but, yeah. All right, any last questions, thoughts? All right, so I'm gonna hand out the quiz, and again, if you wanna take a break, you can take a break. Otherwise, you know, we'll do our routine, so just do your quiz. It's open note. Again, just don't Google for solutions and don't ask your neighbor for their solution. And then you can just turn it in and use this opportunity to ask questions if you're still confused on anything.
On the denominator of the second one in the equation, is the exponent, is that a power of 14?
Oh, and then I do want to try to hand back stuff to you. So I think I left some of your stuff in my office. I still don't have lab 1 graded, just because I've been taking my time with that one. But yeah, if you're wondering where your stuff is, I do want to give it back to you. If you run away, I can give it back. Yeah, I mean, it was over last week. Oh, sorry. Yeah. Like I said, open book, just not, don't Google solutions and don't ask your neighbor for solutions.